Good morning, my name is Nicola Suarez, and I'm the lead for Experiment 4, Vapor Compression and Refrigeration Heat Pump Experiment. This is the outline. We're going to go over the introduction, objectives, theory, the apparatus, the TS and pH diagrams, the sample calculations, and the conclusion. The introduction. In this experiment, we'll analyze the performance of the heat pump. A heat pump is capable of heating a space in cold weather and cooling it in warm weather. In both cases, heat is absorbed at low temperatures and it is released at high temperatures. And we will use thermodynamics at different states to calculate the efficiency of the cycle. The goals is learn how to perform a thermodynamic analysis of a heat pump and how to measure the coefficient of performance, which is the COP, and describe the pH and the TS diagrams. The theory. The COP is the coefficient of performance, which is the ratio of the magnitude of the desired commodity to the magnitude of the expenditure. The expenditure in this case is the electric energy or power which is consumed by the compressor. And the desired commodity or quantity is either heating or cooling. This is the apparatus that we're going to use. There are different cases, but these ones are the 5 main steps. So start the software, switch on AB and AB2 to turn on the evaporator of the condenser, switch on compressor and set approximate value of 40%, adjust the evaporator and heat exchanger flow rate to be 3, 4.5, and 6 liters per minute, and then let the system become stable and while you're taking the data. The components of the refrigeration systems are 4: evaporation, the evaporator, the compressor, the condenser, and the expansion. Cooling takes place first at point A, where there is low temperature and low pressures, and then this cool refrigerant goes to the compressor at B, and at B it becomes hot due to high pressure because of mechanical energy. Then this hot refrigerant goes to state C in the condenser, where it is cooled down because of heat dissipation during condensation, and the heat is released to the environment. And then the refrigeration is expanded to a low pressure evaporation in an expansion valve, which is D, and then that's the whole cycle completes. And those ones are the 4 main components of the refrigeration cycle. What's the difference between an ideal and a real cycle? So the one in this one, in the figure number 4, the one in red is the ideal one, and the one in black is the real cycle. So in practice, the refrigerant enters the compressor at state 1 at superheated vapor, instead of saturated vapor like is in the ideal cycle. Also, the compressor is not internally reversible in practice, which makes the entropy increases as the one in 2. But in the ideal cycle, we can make this refrigerant cool down in the compression process, and will result in a lower state entropy at state 2. This is the TS diagram. This is the TS diagram. I don't know what happened with the arrows, but it doesn't appear on my letters. But okay. So from 1 to 2, it's where the compression happens. Temperature increases and pressure increases. Then from 2 to 3, it's the condensation. Pressure decreases and then it becomes constant. And then from 3 to 4, temperature decreases. And then from 4 to 1, again, is where the evaporation happens. Oh, sorry. This one is the pH diagram. So from 1 to 2 is compression, gain of heat, enthalpy, and pressure. From 2 to 3 is the condensation, loss of heat, and enthalpy. From 3 to 4 is the expansion, decrease in pressure, and no change in enthalpy. And from 4 to 1 is the evaporation, gaining heat, and enthalpy. How does the thermodynamic expansion valve work? The thermodynamic expansion valve controls only one thing: the rate of flow of the liquid refrigerant at the evaporator, and that's the balance equation that they use. P1 plus P4 equals P2 plus P3. The sample calculations, it was a prediction to calculate the COP I took different values from the table. I said P1, it's 500 kPa at the evaporator pressure, and actually the temperatures were in bars, and I converted to Kelvin. So at P1, the T1 is 288.74, then P2 is 1,200 kPa, the condenser pressure, and then temperature 2 is 397.32. And COP is given, which is the coefficient of performance, is given by TH over TH minus TI, while TH is the temperature leaving the gas leaving the evaporator, and TI is the temperature of the liquid leaving the condenser. Plug in those values in the equation, I got a COP of 10.4 in this application. And then as a conclusion, the actual cycle will not be effective as they idealize because due to losses and irreversible processes. That's it. Thank you. Any questions?